my name is Curtis Shoemaker. I'm the project team lead, and this is our team of chemical engineers.
Hi, I'm Lily Hewart, and I am in charge of wiring and electronics.
Hi, my name is Dries Tomoka, and I'm in charge of the bed design and layout.
Hi, I'm Meg Richards, and I'm in charge of data acquisition and programming.
Quick overview of our project. We're sponsored by a Tucson-based company called Hydronaulics. And what this company does is manufacture unmanned surface vehicles used in the water or air for a variety of uses, including search and rescue, military, and police. For our purposes, we are focusing on the boats they make. And the problem that they're experiencing is that when these boats run at high speeds, the motor and electronic speed controller are overheating and burning out due to inadequate cooling water flow rates. So what our design team has been tasked with is to design and construct a heat transfer test bed that mimics the conditions of what the boat may experience and experimentally measure what the minimum cooling water flow rates through these electronics needs to be to prevent any future burnouts. So there's a few requirements that are outlined to us by Hydronaulics to make sure the test bed gets the most accurate data possible. First, the setup needs to mimic the inside of one of the boats. So all of the tubing and equipment you'll see in the next several minutes is of the same type and has been cut to the same size as one of the boats. Secondly, the bed needs to be able to mimic a wide variety of conditions that the boats may see in the field. Because our team is mimicking the worst possible conditions, the tests we're completing are at a high water temperature with a high salinity to mimic poor cooling conditions to find the true minimum flow rate the boats need to never burn up. Additionally, the test bed needs to be able to test a variety of motors and configurations. So the test bed needs to be able to remove one motor and ESC combination and hook up to a different set and still be able to accurately take measurements. And then lastly, the test bed needs to be mobile and relatively simple to use, so anyone at Hydronaulics can use it wherever they see fit.
Here's the overall layout of the test bed. It consists of a data acquisition system that plugs into a computer, the boat electronics, the dynamometer system, the main cooling water system, and the recycle cooling water system.
So getting into the actual design of our test bed. So the cooling water starts here. This is our cooling water drum. Inside is a coiled chiller that keeps our cooling water at exactly the 80 degrees Fahrenheit that is our desired. From that, the water is pumped using that red hose at a varied flow rate, as you can see here, controlled by this knob. The outlet flow rates and pressure are monitored by this analog flow meter and pressure sensor here. From there, the water flows from our outlet right into the motor, as you can see the cooling jacket there, where it flows directly to our electronic speed controller, or our ESC, cooling those both down. And then from there, the water flows into our plate and frame heat exchanger. And from the plate and frame heat exchanger, it flows outlet and is brought back into our tank.
Here are the main electronics that Hydronaulics uses in their boats. There's a battery connected to the electronic speed controller and the motor. For our bed and testing purposes, we have an amp meter between the electronic speed controller and the battery to measure the amps. We also have a servo that attaches to the electronic speed controller, which controls the motor speed during testing.
For the heat exchanger network, cooling water comes from this big tank at about 60 degrees Fahrenheit. The flow of this water is controlled via this spigot right here and sent through the black hose down to our heat exchanger on the test bed. It is a plate and frame heat exchanger from Razapack. We monitor the flow rate coming through with this flow meter, and then water is recycled back through the system.
In order to replicate operating conditions for the boats, we attached a hydraulic dynamometer to the motor. In the dynamometer system, we have a sump pump to supply water to the dynamometer, recycle streams that feed back into the dynamometer water tank, a scale to measure the force, and valves to adjust the pressure in the dynamometer, which changes the load produced on the motor.
There are 4 probe thermocouples located on the test bed and 2 stick-on thermocouples, one on the motor and the other on the ESC. There are also 3 digital pressure sensors used in the bed as well. The output for these is a voltage, which is then converted to a pressure. All of the thermocouples and sensors are connected to 2 data acquisition boxes under the test bed. These are then connected to a computer where the real-time data is displayed and recorded.
To conduct these experiments, the team applied a large load onto the motor using the dynamometer to simulate conditions that might cause motor burnout. At the same time, cooling water was pumped through the system at a variable flow rate.
Temperature data was then taken from the system using thermocouples before and after each electronic to gather heat transfer data, as well as the temperature of the motor and ESC using stick-on thermocouples to try to find the minimum flow rates needed to cool the motor sufficiently.
The main safety concerns in our system were the dynamometer and high pressures causing tubes to disconnect. However, when testing the dynamometer, it was found that it produced very little force and would not be a safety risk. Regarding the high pressures, we used tube clamps to ensure they would sustain when running. Additionally, there was always a team member operating the pump and ready to shut it off if any tubes happened to disconnect.
An additional safety element that the team had to consider was that the motor and ESC would potentially operate at high temperatures. As a result, at the beginning of the semester, the team filled out a JSA with the location of all the fire extinguishers and safety equipment throughout the chemical engineering lab. Additionally, the team utilized proper PPE to remain safe during all of our experiments.
When running the experiments, it was determined that no amount of cooling water was sufficient to keep the motor and ESC cool. Running at 1.5 gallons per minute of cooling water and 50 amps, the electronics reached 45 degrees Celsius. However, the cooling water increased by less than 1 degree Celsius, meaning very little heat transfer occurred between the electronics and the cooling water. After running for 3 minutes, the motor started smoking and the experiment was stopped. Since the temperature sensors are on the outside of the electronics, we suspect the internal temperatures were much higher and above the operating limits. It can be concluded that inefficiencies in the cooling jackets of the motor and ESC are the limiting variables, and insufficient cooling water flow rate is not the cause of motor and ESC burnout.
There were 3 main lessons learned by the team over the course of the project. The first was how to conduct experiments to size equipment. In order to know what size pump was needed for the system, our team had to run experiments to find out the pressure needed to circulate water around the entire cooling network. The second was learning how to build something from scratch. We learned the significance of organization when making a parts list, how to use different tools, and the importance of working in parallel, not just series. The third and final thing we learned was how to effectively troubleshoot. Throughout this process, we learned how to approach a malfunction and look at each individual component to locate the root cause of the issue.
Special thank you to our hydronics liaison, Dylan Allen, our project mentor, Dr. Greg Ogden, and our overseeing professor, Dr. Kim Ogden. We could not have completed this project without you, so thank you all. An additional special thanks to all of the chemical engineering faculty and staff. Thank you for listening to our presentation, and we hope you enjoyed it.